Okay, hello everyone. So today I'll go through my final project for embedded systems module, which is an embedded feedback control for temperature regulation. This is the artifact report for the same. So an overview in many small scale environments like food storage labs or bakeries, server closets, etc. Uh, Precise thermal regulation is crucial. So off-the-shelf smart cooling solutions will lack customizability, cost efficiency, and transparency. And this project was developed to solve all those problems, and it will leverage a custom PID library to fix these issues. So the existed previous implementations in this space, they rely on proprietary hardware or cloud-bound solutions. There might be privacy cost or latency concerns. My system will be fully offline, open source, and controlled locally with transparent logic. So how can we build a low-cost customizable temperature regulation using embedded devices that ensure real-time control, robustness, and remote configurability? That's the problem statement that I'm trying to solve with this project. Requirements will be accurate temperature monitoring, visual local feedback via OLED display, PID controlled fan regulation based on real-time data, communication between microcontroller and the Raspberry Pi, uh, a web-based dashboard for monitoring and set point tuning, some fault-tolerant and safe shutdown mechanisms, the design principles, what the system is built on the basis of. So clear separation between sensing, control, and UI. Transparency, all logic is open and viewable. Responsiveness, there is a real-time fan speed adjustment based on the incoming sensor data. Sorry about that. And reliability, so safe signal handling, deadband, and clamping mechanisms that I'll get into later. So the hardware components are Arduino, the IoT small node, or DHT11 sensor, an OLED display to show the workers working nearby what the real-time temperature is. Raspberry Pi 3B Plus will run the PID loop and HTTP server. A PWM cooling fan that will be driven by GPIO 18, a Wi-Fi router. So we need Wi-Fi to connect these devices to each other. So the HTTP post and GET request will work properly. So for the demo setup, this is how the hardware will look like. We can see the OLED display, the temperature sensor, and the fan will simulate smart AC cooling. For this demo purpose, I've used a not so powerful fan, but in the real world, I would prefer having a proper cooling unit that the Raspberry Pi can directly send PID output to, and it will have a more proper impact on the temperature. But for a demo purpose, this is what I have built. The communication flow, Arduino will send HTTP post with JSON payload to the Raspberry Pi server. PI will pass the temperature, compute the PID output, set PWM duty cycle, and our dashboard will allow us to set a set point and do some visual monitoring as well. This is the system overview diagram for the same. So as I mentioned, the Raspberry Pi will host all these things, and the mobile browser will help us control the set point, which will enable the PID controller to generate what should be the cooling temperature in order to get the current temperature closer to the required temperature set by the user. So the system overview diagram conveys that. The flow diagram is just this in a more simplified way. Arduino connected to THT sensor OLED display and HTTP client. Raspberry Pi hosting all these things. And it simulates a REST API client that the mobile browser that the user can interact with through the mobile browser. So we can send get post request for the temperature set and get, and we will simulate cooling through the smart AC unit into the room. So this is the link to my code. I'll get through it. Yeah, so a general overview, which I already covered, the hardware architecture, way the hardware has been set up, a more in detail explanation of all the wirings completed in order to get the setup working. Software architecture for the same. We need to first initialize all these libraries, and this is what the example payload will look like. On the Raspberry Pi, we use the HTTP lib library to host a simple lightweight server, and all the set points are handled by different endpoints, and the temp set point will help us update the PID loop. And the slash set point post will allow us to, so the update set point button will throw a slash set point post, and we will be able to update real-time temperature desired. so that the PID controller can start working on it. So this is what the dashboard will look like on the browser when we go to the Raspberry Pi IP address and the required port. So what is a PID? It's an automatic control algorithm that is used in most industrial solutions. It proportional the P stands for proportional, so response to current error, integral response to accumulated past errors, and derivative will predict the future error trend. PWM is a method of simulating analog control using digital signals, so we switch power on and off rapidly, and this helps us simulate like a continuous voltage level. The period used for this is 40,000 nanoseconds, which is around 25,000 times every second. So that many PWM cycles uh, will happen in 1 second when our fan works. And the duty cycle is the proportion of the period where the signal is high, that is the power up. This will help us control the speed of the fan. So suppose it's 10,000 nanoseconds, that means 25% duty. So low fan speed, that's 1/4 of the time that the fan will stay on. So we simulate, it's not exactly 1/4 of the time, but with 25% duty, so the speed can be controlled. It will be 1/4 of what its full speed is. So accordingly, 20,000 nanoseconds, 40,000 nanoseconds, and so on. And once we update the set point, we can see in the graph that the desired temperature starts hovering down closer to the desired set point, which is 24 degrees Celsius, and it will eventually reach that. So some fault tolerance features. So we have a deadband to prevent overreaction near the set point. So if you get close, we don't want it to fluctuate too much. So we just set the fan control to 0 immediately. We do some integral clamping. So this helps avoid excessive buildup during saturation. So if there is continuous error happening, then the PID will keep accumulating that and it might overshoot or undershoot later. So integral clamping avoids that. There's graceful shutdown. So any issue with Raspberry Pi or Arduino, the fan's PWM signal is automatically disabled through a cleanup function that I personally wrote. And we will go back to the default 50% duty cycle, which is the, let's say, the manufacturer's default cooling stage. So it will go back to default working, even if both nodes start shutting down or some issue happens. This is done with the help of signal handlers. So they ensure clean fan disabling on SIGINT or termination. SIGINT is more explicit, like a control C directly, which I have tried and tested so that I could ensure that on termination, whether it works as expected. So how it works, sensing will read the temperature, show it on OLED. Communication, Arduino will send JSON temp to Raspberry Pi. Raspberry Pi will compute PID and adjust fan PWM output. Monitoring web dashboard will reflect all these live values and allow us to do any set point tuning if we wish to. The setup instructions, these are covered in the PDF as well. So on the Arduino side, this is what the output will be at the start, and we start getting the temperatures one by one. On Raspberry Pi, we need to install and configure all these libraries, generate our executable with C++17, link all the external libraries, and once we start running, we'll start seeing this output. The HTTP starts running on port 8000, and we start immediately getting the received temperature from Arduino. And once we set the set point, like suppose up to here, we can see set point updated to 24 degrees Celsius, the PID loop will run into work, and then we start generating the PID output and the fan duty. So essentially the speed of the fan, and slowly will eventually reach the desired set point, which was 24, and the fan duty will immediately uh, have the dead point enhancement working, and it will go to 0. And this can be visualized through the graph as well. So from the final output, we can see that OLED and serial log real-time temperature. Fan automatically adapts speed to reach and maintain the set point, and a dashboard will show all the trends and allow us to do any dynamic configuration. All the components are modular, responsive, and fault resilient. This is ideal for cold storage automation, cafes, restaurants, bakeries, laboratories, or indoor horticulture setups. I'll go through a demo video so that it's more clear how the project works. So let's say we're here, and this is the desired temperature, say 24. I updated it here as and this the blue line is what the actual temperature is. You can see here the set point was updated to 24 degrees Celsius, and now the received temperature and PID output help us generate the proper fan output. Oh, here we can see the temperature continuously changing and updating as per the specification. Oh, yeah, and the loop keeps running until we reach the desired set point. We will keep getting values on the terminal. This is for debugging purposes only, but the graph is also updating at the back. As you can see, yeah, we're getting closer and closer to the desired set point, and the fan also has reduced its speed now as we're getting closer and closer to the set point. Yeah, as we reach the zero cycle, the PID output goes down to zero, and the fan was shut down almost, like it's shut down when we reach zero, and that's it. We reached the desired set point. So that was the demo. Yeah, and so I've tested this manually, the functional validation. So I've ensured that Arduino sends accurate temperature values every 2 seconds. The OLED display was checked whether it is displaying the correct temperature. Uh, I manually applied heat to see if there was any increase in fan duty cycle, and I confirmed that the fan speed gradually reduced and eventually reached 0%. So we can verify the effectiveness of thread-dependent PID clamping logic. The system can run for long hours without any issues. I personally tried for 3 to 4 hours and still worked perfectly fine. Uh, the communication fault from Arduino and from Raspberry Pi is handled via the default signal handling. And so we go back to the 50% PWM, which was as per say market specification to keep the general cooling still working. And the dashboard will work across many different popular browsers, Chrome, Firefox, Opera, anything which have JavaScript enabled. So the user manual for the same. This is the same setup instruction and the same output that I went through on the GitHub README. Oh yeah, and we eventually reached the temperature video. Yeah, so upon further discussions in the seminars, I was told to add like a few modes so that the users can have more control over the PID logic. So I have added an energy saving mode and a performance mode. So energy saving mode has smaller values so that we keep the fan off for a longer period, thus saving energy. And uh, uh, so we keep low demand conditions for energy conscious environments. And a performance mode where suppose uh, uh, if we need extreme cooling immediately, we can maximize responsiveness and span speed for rapid cooling. So for high demand scenarios like cold storage or laboratories or some peak hours, we can use the performance mode if we wish to, and the users can switch them accordingly. Yeah, so it will sort of look like this now. We'll have an energy saving mode and a best performance mode, and it will change the PID values accordingly. So also I added a simulated casing. So in real world, we only want the LED to be visible, not the DHT sensor or the wirings. So everything will be covered in a proper casing. A better video for that is, yeah. Yeah, so everything is covered in a proper shelling and we only see the temperature that is being updated. Yeah, that's it. Yeah, so my conclusion and reflection, this project has deepened my understanding of embedded communication, HTTP protocols, and PID feedback design. One major challenge was synchronizing everything and avoiding any race conditions, but I resolved that with proper set parameter tuning and some high precision clocking synchronization across the project. Uh, some reconsiderations I could make if I were to do it again was to add some sort of persistent storage, like maybe a TB or even on in-memory storage, uh, or even explore MQTT for more scalable communication. But with if you have a Wi-Fi in the workplace or where you're hosting these products, I don't see any reason to use it because Wi-Fi works perfectly fine with get and post and some UCD principles. So user-centered design. So visual feedback by OLED for immediate temperature awareness so that workers working nearby, they can immediately see the temperature, whether it's good or bad, and they can still have manual, let's say, they can override certain conditions and still have complete control there. Like if this can be done via the visual feedback to the OLED. And if you have a phone or a device, anything nearby, you can use the dashboard to set the temperature for more intuitive temperature control. Very simple for messaging and serial logs in the UI. You can use that for debugging or fixing any issues later. And there is minimal setup overhead for any non-technical users. They just need to update the desired set point, choose a proper mode that fits their requirements, and that's it. The PID controller and the project will handle the rest for them. That's it. Uh, that's it for my project. I hope you liked it. Thank you.